So that's all.
I love it. No.
Good evening, everybody. Thank you so much for coming out to our Labcorp Leadership and Technology Speaker Series tonight. I'm Leslie Rand Pickett, and I'm the Interim Director for Engagement and External Relations for the Department of Computer Science. And we're really glad to have you here tonight for our talk. This is the 18th year of this seminar series, so we're really excited that we have, over the years, brought wonderful speakers to talk to our students, to our community, folks who have roles in leadership, who also come from technical backgrounds, so really to give you all a great idea of some of the different things that you can do over the course of your career as a technical student. So this is our first Labcorp talk for this year. We will have one in the spring as well, in February, and I hope you will come back and join us for that event later. But we really just want to thank our Labcorp sponsor. They have been a partner with us for a few years on bringing this lecture series, so we want to make sure that we thank them for their support. Certainly we're going to ask, please, I know you guys don't have cell phones on anymore. It's not something we need to say to students usually, but don't forget. Make sure that we don't have notifications going off during the talk today. And you may have noticed there's cameras around. We are broadcasting the talk tonight via YouTube Live, so you can go back, rewatch all the exciting things that you learned from tonight. I'm sure you're going to want to go back and do that. And we also have some students who I know are looking to get credit for attendance at a seminar. I've had a couple of you ask already. If you've got a form that you need me to sign, I'll be glad to do that at the end. Also for our PhD students in computer science, we have a student and over here on this side, yes, she'll be happy to swipe your ID so you can get your attendance credit for that. If you are in our YouTube audience and you need to check in online for your seminar credit, there's a link in the program description that you can fill out your attendance form for today. So it takes way too long to tell everybody to do that, sorry. Okay, so the Labcorp Leadership Series really was created to give students from all different disciplines some exposure to leadership topics in technology. Tonight, we are going to talk specifically about artificial intelligence, real impacts, meteorology in the era of AI. We're very honored to bring Nate Johnson as our special guest speaker tonight. And Nate is an alumnus of our computer science program, so we're really excited to have you back, Nate. You'll notice when you exit this classroom at the end of the program, his photo is on the wall as part of our Faces of Computer Science, so we're very proud to have him as an alum. He is currently the Vice President of Weather Content and Operations for NBCUniversal Local, where he guides strategy and innovation for weather coverage across 44 English and Spanish language TV stations across the country. He leads more than 120 weather professionals nationwide, setting standards, identifying best practices, and providing the tools and techniques that they need to provide the most accurate forecasts on TV, web, apps, and beyond. Nate also coordinates the group's climate reporting and collaborates with technology operations and digital teams on projects ranging from radar systems to app and website development. Also recently, he was appointed to the Editorial Operations Council for AI with NBCUniversal. Previously, he was a meteorologist and executive producer at WRAL TV, which is right over there. You guys probably pass it all the time, traversing between main campus and Centennial campus. His work has earned him 4 regional Emmy Awards, 2 national Emmy nominations, a DuPont Columbia nomination, multiple Associated Press and Edward R. Murrow Awards. Very distinguished. Awesome. He's a past president of the National Weather Association, a holder of both the American Meteorological Society's Certified Broadcast Meteorologist designation and the National Weather Association's Seal of Approval. Most importantly to us, he's also a member of our Computer Science Alumni Hall of Fame, so we're very happy to celebrate him, and please join me in welcoming Nate Johnson.
Thank you, Leslie, and thank you for the warm welcome, and I want to thank the department and Labcorp for the opportunity to come back to my alma mater and talk about geeky things, because I love weather, I love computers, I love technology, and goodness knows we have a lot of it here at NC State. I want to start with a little bit of history to set the table a little bit. This dashingly handsome fellow here is Jacob Bjerknes, and he and his father, Wilhelm Bjerknes, both Norwegians, helped to essentially create what the science of meteorology as we know it today. Both were geophysicists. Jacob, the younger Bjerknes, was sort of pressed into service when an older grad student was called to the front lines of World War I and unfortunately was killed. So he had to jump in and actually took over studies and studied with his father for a long time, both in Germany and in Norway. And it is to them that we owe the privilege, I guess, of knowing what we know about the way frontal systems and air masses move. And in fact, the term front, like a cold front, which is the leading edge of cooler air, or warm front, leading edge of warmer air, actually is a connection to the battle lines in World War I. As they were looking at some of the maps and things, they said that these air masses and the boundaries between them, these discontinuities between air masses, looked and behaved a lot like the battle fronts that you would see in Europe in World War I. And so that's where we get the terminology cold front and warm front. There's actually a wartime connection to that. One of many wartime connections between meteorology and meteorology forecasting and World War I. And in fact, this is a frontal map I stole off of the Weather Service website yesterday, showing the cold front that moved over that brought us all this nice weather today, the area of high pressure. And you can imagine that being sort of the battle zone between colder air and warmer air. You've probably heard that a couple of times watching television. These thunderstorms formed on the battle zone between cold and warm air. That is essentially, again, a throwback to the Great War, the war to end all wars back in World War I. And if you look at those side by side, you can really see that pretty clearly, that correlation there. It's interesting because the younger Bjerknes, Jacob, or Jack as they called him once he came to the U.S., was saw this pattern play out. And when we think about weather, a lot of times we hear the phrase weather pattern. When we teach it to young kids, we talk about weather patterns. We're in a snowy weather pattern. Early next week, we might be in a rainy weather pattern, an unsettled weather pattern. We talk about weather in terms of patterns. Well, as it turns out, that also dovetails really nicely with the topic of tonight's talk, because artificial intelligence, a lot of AI, is really about pattern recognition and manipulating and studying data to find patterns. This is just one definition of many. I grabbed a snapshot off of the web, but the theory and discipline of programming computer systems to learn from and spot patterns in data sets. So in a sense, meteorology, the birth of meteorology going back, the modern meteorology anyway, going back more than 100 years, was because a couple of people noticed patterns in the atmosphere, and now we're talking about noticing patterns with artificial intelligence. So AI, for those of the computer scientists in the room, you know that AI is a buzzword. You probably hate hearing it at some level because what kind of AI are we talking about? Is it machine learning, deep learning, large language models, generative AI? There's all these sorts of catch-all, of these words that fall under this catch-all term of AI. And we can use a lot of these when we're thinking about computer modeling and forecasting the weather. But one of the things I want to talk about is the fact that AI at its core is pattern recognition. It's also automation. There's a way just to think about as AI as a type of automation beyond the capabilities of what we've been able to do up until really the last 10 or 15 years. Well, when it comes to automation, one of the things I love about computer science and meteorology is there's a lot of overlap between these two sciences. I think they're probably two of the neatest majors to put together, and I double majored in both when I was an undergraduate, because there's so much application between the two. And when we think about automation, pattern recognition, things like that, machine learning, meteorologists have been doing this for decades. Literally for decades. This is a paper that was published in 1972 documenting something that had actually been in production in the 1960s. It's called model output statistics. And the idea being that they could look at model data, this raw model data at various levels of the atmosphere at various grid points, and then correlate how the models, the data over a course of a number of years, correlated to actual real conditions on the ground. So you could take the model data and then look at the MOS to figure out what the model actually would think the high temperature would be based on not just the model data itself, but recent model performance over a course of a number of years. So we've been doing this automation thing for quite some time in the meteorology space, and so I think AI is sort of a welcome innovation, something that we get to play with and have fun with. So I want to talk a little bit about a brief history of numerical weather prediction, again to sort of set the table for how we're going. And we go back to the elder Bjerknes, Wilhelm Bjerknes, who came up with a number of what we call the primitive equations that govern airflow and movement in the atmosphere. And he came up with these in the late 1800s, published them in 1902, with the explicit prediction that we would be able at some point in the future to predict the weather using these equations. So if we had a good understanding of the initial state of the atmosphere, we could then run these equations, run the math through these equations, and then come up with a future state of the atmosphere that would be a prediction of that. Unfortunately, that was not within his contribution. We have to look about 20 years later to a gentleman named Lewis Fry Richardson, who was a Quaker, a pacifist. He was a medic during World War I. And after he finished, he had come up with this idea of taking these primitive equations, figuring out how to manipulate some of those equations to put data into them and actually run a forecast. And his story is really interesting because the first weather prediction, numerical weather prediction based off of all of these equations, it was a 6-hour forecast. It took him 6 weeks because he did it by hand. It took him 6 weeks in 1922, and it was horribly wrong. It was not constrained by any sort of physics or anything, and there weren't any bounds, and so we wound up with pressure differences of almost 150 millibars, which is kind of like the difference between standing on the beach in Wilmington and standing on the top of Mount Mitchell. That's a pretty big difference over 6 hours. The kind of weather that you would have experienced with that kind of pressure change, none of us would be here talking about it. But his idea, one of the things that he fleshed out, was this idea that we would have computers, people, think of this in the hidden minds type, where you have people running the math back and forth. And he had envisioned this almost stadium, a room full of these people. You would have a conductor in the middle, and the conductor would help to organize and move data from point to point. And so each person would sit at what we would call a grid cell or a grid point in a computer model, vernacular today, and they would run the math, and then the spotlight would move to the next, and they would pass the data from back and forth. It really was almost dystopian. Like, it was this very wild notion of The number of people, if you look at all the people on the sides of this thing, like this was, probably 20 stories tall. This was actually an artist rendition back in the 80s of some of Dr. Richardson's ideas. And it really was sort of a fanatical thing. And unfortunately, between the forecast not working out very well and some of his sort of crazier ideas, he was not well received in his time, unfortunately. But he is really one of the founding fathers of numerical weather prediction. Now, one thing he got absolutely right, and the idea that the amount of computing technology, if you will, that was required to do this would at some point fill a room. And the computer scientists in the room know this picture. This is ENIAC. This is one of the first true, what we would, at the time call a supercomputer. Pretty amazing piece of technology. And in 1950, they were able to program ENIAC to run a computer model forecast of the atmosphere. It's one of the first, like I said, the first time that we actually did a numerical weather prediction on a computer. It still took longer than the weather. So the forecast actually took longer than it actually got to get to the weather, but the results were actually pretty useful. And Dr. Richardson was still alive at the time, which is amazing, and they reached out to him and shared with him, he was an older man at this point, shared with him the fact that this idea that he had conceived had actually come to pass, and that the forecast worked out very well. You can imagine the sort of validation, right, that this guy had felt after 28 years of basically being ignored and whatnot. Like, his idea turned into fruition, which is an amazing thing. And of course, some things never change. This is Dogwood. This is one of the two supercomputers that the National Centers for Environmental Prediction use today to run the computer models that you see a lot of them on TV. If you hear about the American model, that's run on this computer. There's another one, an exact duplicate of this machine in Arizona. It's called Cactus. They are duplicates so that they're different parts of the country so that there's continuity of operations in the event of some sort of natural disaster. Almost 15 petaflops of computing power on this system. It's a pretty intense piece of equipment. That's, I think, on the order of 1 trillion times more compute power than it took to send man to the moon. So this is a pretty beastie machine. And it was actually upgraded, got about 20% more capacity a couple of years ago. So they're very proud of this. But if you think about it, you go back, there's ENIAC, takes up a full room. Here's Dogwood, takes up a full room. Some things never change, although the compute power certainly has. So NWP now, a very different thing, but built on the same foundations that Dr. Richardson had come up with a little more than 100 years ago. It starts with raw data. It starts with observations of the atmosphere. And if you think about going to the airport, watching on, you see on TV, they say, at the Raleigh-Durham International Airport, it's 85 degrees, with the wind out of the south at 7 miles per hour, right? Surface observations, we take hundreds of thousands of those every day across the globe. So all of those are collected. We have satellite data. The amount of satellite imagery and information that comes off of these satellites is absolutely crazy. And so we collect a ton of data via satellite that we're able to use to feed into the models. We have upper air soundings. The image on the upper left is a trace of a balloon as it goes up through the atmosphere, taking temperature, wind, dew point, moisture measurements, so that we have a sense not just of what the air is here at the bottom of the ocean that we call the atmosphere, but all the way up through the atmosphere, because we know that the weather patterns that happen above us affect us here on the ground. So we collect all of that data, and there's tons more of it than I could possibly fit on a slide. Hundreds of different types of data, hundreds of sources, but we collect all of that. And then all of that is run through a process that we call data assimilation. We have to take all of these irregular data points, right? The airports are not evenly spaced out, and we have to do an analysis to get those onto some kind of a grid, both in terms of horizontally across the land surface, but also vertically through the atmosphere. So that process is called assimilation, and it is we've just in the last 10 or 15 years really come to understand how valuable and important this process can be in getting your model off to a good start. Once you have that data assimilation done, you have what we call an analysis. That's our first guess. That's the initial first guess. This is what the model thinks or is working off of as the current state of the atmosphere. And then we will take those equations that you saw and apply those equations at each grid point in the grid, whether it's a limited grid or whether it's across the entire globe. We feed that into the computer. We crank all of the data, we advance it forward, and then essentially you'll take the initial guess, you'll run the equations through to come up with a time step, a couple of minutes into the future, and then you'll run the same equations on that as your initial guess, and you'll do that all the way forward, in some cases out to weeks at a time, to come up with the forecast that you would see. Meteorologists would look at something like this, where you see these postage stamps of what the weather might look like going forward. We would use that to come up with the forecast that we would see in your apps, on your websites, on TV, that sort of thing. So, one of the other things that we found is over time, we've learned that run-to-run stability, so if you run a model 4 times in a day, one of the things that we found is that we have more data at some times than at others, so we do balloon launches twice a day, not 4 times a day. So one of the things that we can do to help the models from getting too jittery and keeping the solution sort of on track is to take this model output from the first forecast step and then feed that back into the next model run's analysis. So that's a way to help us stabilize the model. It's called cycling the model. So we take that data from the output from one run and we feed it in as input to the next to help the model sort of get going, especially in those off-hour runs where we don't have the upper air data, for example. Now the fun thing is, AI is already touching pretty much every step on that previous slide, and we'll talk about that in some detail. In this analysis step, one of the easiest things that you can do, this data assimilation step, one of the easiest things that you can do is to treat the data as sort of a big data problem and then use AI to identify things that don't fit the pattern, that don't make meteorological sense. And one of the best examples of this, about 10 years ago, IBM, there's a division of IBM called the Weather Company, and they spun up a model called the Graph. And that secret sauce to that model was using pressure readings from everybody's cell phone that had the Weather Channel app, because they're all one company at the time. If you had the Weather Channel app on your phone, you could give permission for it to take readings to determine the atmospheric pressure at your given location and feed that in. That's one of those fundamental variables that it's really nice to have a good handle on in that initial condition. Well, you can imagine that in places like New York City, that could get really wonky really quick, because if you're taking your phone to the top of 30 Rockefeller Plaza, for example, you're going to be going up 60 floors. You're going to be in an elevator which has some weird pressure things to it to begin with, and then you're getting to the top, and the pressure might be substantial, might be significantly different, enough to throw off the model if we treated that as just a surface observation. So you could use AI to just look for different types of data that just don't make sense, that it's clearly bad data. Every now and again, one of the balloons that we launch will get thrown off, and some of the data comes back weird. So there's ways for us to look at that and clean that up. But there are also a number of different full-on data assimilation schemes that are being looked at and based upon an AI foundation. There's a number of them. And just in the last couple of years, like these papers are all just in the last 2 years worth, where we can take data and use AI approaches to actually generate the analysis, so it'll go from raw data to just the analysis without necessarily doing some of the objective analysis where the computer would have to say, well, this data point isn't on a grid cell, but it's 5 kilometers south of that cell and 8 kilometers east of that cell, and doing the math to figure out what the influences is, which is what normally happens. We can actually use AI to identify patterns and to come up with that. Satellite data, the amount of satellite data, again, is tremendous. We've just launched a couple of new satellites, new geostationary satellites in the last 10 years. GOES-R, GOES-S, GOES-T, and GOES-U will be coming. So these are the 2 satellites that most of the time, if you see a satellite picture on TV, it's coming from GOES-S or GOES-T, depending on whether it's east or west. Those satellites collect not just the cloud images that you see, but there's 16 different imagers, plus a number of sounders and other equipment on the satellite that we feed into the models to understand what the initial state of the atmosphere is. It's a ton of data. There are some repeating patterns that we can jump into, and AI can certainly help with cleaning all that, with not only collecting all that data, but cleaning all that up and then giving us an analysis that we can feed to the model that's going to be coherent, that will make sense, that's meteorologically and physically sound, and we feed that in and go from there. The next step is the compute phase, and this is where I think we've seen just a tremendous amount of growth, again, just in the last few years. GraphCast, there was a couple of years ago, the team at Google produced a GraphCast model. And GraphCast is based on a graph neural network foundation, the idea being that you come up with you do your training on analysis, reanalysis data, and we'll talk about that in just a minute. You train on past weather, basically. Say, here's what weather looks like. And then you start with your current weather and you pass it through your graph neural network to come up with the next step of data, and then you do it again and again and again, and you come out with a forecast that would run out some number of forecast hours going forward. This takes on the order of, if you were to train it on one TPU processor, this is going to take you on the order of a couple of years to train. Now, typically they would throw a couple, 3 dozen of them at this and train it in the span of a month or so, but the training costs are significant. This is not anything that we can just sweep under the table. But once you have trained the model, you can do a full forecast out to 10 days in a minute. Now, put that into perspective. The American model takes hours to grind through the physics, these partial differential equations that we've applied numerical methods to get them to fit into the computer, right? Because the computer can't solve partial differential equations by itself. We have to help it out a little bit. It grinds through this and takes hours to do the initial data assimilation and then to run the model out for 10 or 14 days and then to come up with the data that you would see on TV and that we use as the foundation for forecasts. So to be able to run this in a minute is that's stupid fast, right? That's amazing. The Europeans, so we have the American model, right, which is the Global Forecast System, or GFS. The Europeans also have a model, and that is considered to be the gold standard of especially medium-range weather forecasting, and that days 3 through 7. So not today, tomorrow, but the rest of the 7-day forecast. The Europeans are considered to really have the edge overall in terms of an average. They also have created an AI forecast system. They call it AIFS. That is also a graph neural network-based forecast system, but it also uses neural operators and vision transformers to do its math. It can run a full forecast out to, I think, 2 weeks in 3 minutes. Again, training on this is taking on the order of, on a single processor would take you on the order of a year or 2. They'll run the entire model on a single TPU processor in 3 minutes, which again is absolutely amazing because I have some meteorology students here in the front row, and they know that when the time shifts, we get the model data sooner because the model data is all run on essentially Greenwich Mean Time, which isn't affected by daylight saving time. So when we shift back to standard time, the model data all comes in an hour earlier, which is really good when you're up late wanting that overnight European model forecast to come in to see how much snow we're going to get the next morning or the next week. So being able to imagine not having to wait until 11, 12 o'clock at night, but as soon as the model starts to run, you collect all the data, you do your DA, you feed it in, and then you're getting the model run in 3 minutes. So instead of waiting until midnight, you're getting it at 7 o'clock, 7:03 basically, which is kind of wild. And then last year, right before the American Meteorological Society's annual meeting this year in New Orleans, the Google DeepMind team blew our minds because in less than 18 months after they had released GraphCast, they produced GenCast, which is an entirely different way of looking at and approaching this problem. And it's interesting for a couple of different reasons. Number one, we've gone from a neural network-based type approach to essentially image processing. So this is the same type of technology that generative AI technologies like Sora, which is that new video generation app, this is that same kind of thing where you start with, you train the model to denoise straight noise into weather. And so you start at the top, you train it on actual weather, and then you give it noise. and then over 40 passes of this denoising algorithm, you come up with an image of the weather that looks meteorologically coherent. They can run not just a single model, but they can run this model in full 51 times in 8 minutes. So not only do you get what we would consider the deterministic run, this is just the model's best guess, but we also can perturb the initial model fields ever so slightly because we're humble. Mother Nature keeps us humble. We do not know everything about the way the atmosphere is set up at any given moment, right? I know, for example, what the temperature is at Raleigh-Durham International Airport over next to runway 23 right at any given moment. I don't know what the temperature is on the other side of the airport. I don't know what the temperature is in Garner. I don't know what the temperature is in Rocky Mount. There's an airport at Rocky Mount Wilson, but that's not in downtown Rocky Mount. So we don't know everything about the atmosphere, and so we acknowledge that. And as a way to try and compensate for that, we will then nudge the initial model fields, or we'll run a slightly different set of physics, and we'll run it over and over and over again with these different perturbations to come up with what we call an ensemble. And the idea being that if we run it 50 times, and all 50 of those solutions all converge in the same direction, then we can have higher confidence. We think that the atmosphere is in a more predictable state, and we have higher confidence on the solution that the model is coming up with. On the other hand, if after a couple of days, the hurricane tracks look like a bowl of spaghetti, and you've seen these spaghetti plots on TV that call them that, if it looks like a big bowl of spaghetti, then maybe we shouldn't have so high confidence. And it's giving us maybe the range of possible solutions, but at the end of the day, it's telling us, hey, the atmosphere is not in a very predictable state right now. And that's important for us to know, because then we would perhaps not put as much stock in a single solution, but we would be able to then understand a little better about the range of possibilities. So we can do an entire ensemble run, again, in 8 minutes. With the GFS, we have to run the operational run at full resolution, and then we sort of dumb the model down a little bit. We take the resolution, we make it coarser, and then we run it the other 49 times to come up with the ensemble runs, which introduces a potential source of error. Is the ensemble, if the operational is doing one thing and the ensemble means doing something different, is that because the ensemble is catching on to something? Or is that because the ensemble is running at a lower resolution and the particular feature that we're interested in, we're only capturing in the full resolution version of the model? We don't know. We have to sort of take a stab in the dark at that. But really fascinating. Again, 8 minutes for an entire ensemble run, which is crazy fast. And this is another, there's a paper by Shin et al. From just last year. These are a number of other entities or entrants in the what we'll call machine learning or AI weather prediction game. And you can see there's a range of different approaches. There's vision transformers, graph neural networks. There's cross-modal fusion transformer. I won't even pretend to tell you what I think, what that is. Really fascinating range of stuff. But one of the interesting things I want to call out on this graphic, notice who some of these sponsors are. Microsoft, NVIDIA, Google. You have these compute companies who see now, this is a really great application for all of this AI tech. AI is the buzzword in Silicon Valley. They want to spend, we find all kinds of people to spend money on AI. We're building data centers everywhere, all of this stuff. This is a great sort of showcase because the weather affects everybody. And it doesn't just affect everybody, but it can cost people money. It can hit you in your wallet. So if you have a drought in California, prices for things like avocados and almonds are going to go through the roof. On the other hand, if you have floods in Florida or a late frost in Florida, it's going to kill the citrus, and your citrus prices are going to go up. It's going to cost you more to have that glass of orange juice in the morning. So some of these tech companies that are trying to push their AI solutions are looking at weather as hey, this is a great way we can run it. There's clear applicability to it. And this is a way that we can sort of push our AI stuff into the public consciousness, which is really cool. And then finally, I want to talk about the communication piece of this, because this is where I sit. When I was an undergrad, I spent some time doing the stuff on the right. Now that I'm in broadcast and the communication piece of it, I really spend a lot of time on that bottom left-hand corner, whether we're putting our data out into apps or whether we're using television and radio and social media to communicate this. And there's been a couple of really interesting developments in the last couple of years about this. One is a meteorologist who used to be on the air in New York City. She worked for Fox Weather for a while. Her name is Amy Freeze. That's actually her real name, Amy Freeze. You can't buy names like that. And she has a website, amyfreeze.ai, and she's partnered with a tech company. She has digitized herself, turned herself into an avatar, and is using generative AI to look at weather forecasts, to generate scripts, and then to have her avatar deliver these weather forecasts in front of maps that are automatically generated. So something like this was presented at a weather meeting a year and a half ago, and actually the next example was part of that, and the room absolutely flipped out. It's like, you're going to replace me, oh my God, right? That's a thing that's being done, right? It's not being done widely, but we have somebody who's playing with that in that space. And she said, she was interviewed, and she's like, this extends me. This allows me to be in places where I could not be, whether it's because of the volume of recording that we have to do to be able to be hyper-local. So not just to give you a forecast for the Northeast United States, but to give a specific forecast for the Upper West Side of Manhattan. Like, that's the kind of thing, if you can digitize yourself and you trust the technology, you could actually have it give a custom forecast for every zip code in the United States, potentially on demand, which is a neat thing. This is AI. This is an application of generative AI. This was the example that actually blew the minds at the NWA meeting last year in Irving, Texas. The weather company, or the Weather Network, which is essentially the Weather Channel in Canada. It's a company called Pelmorex. And they're not only running their own internal in-house AI model that they're using in some of their forecasting, but they've also taken one of their presenters. They have, with her permission and with her blessing, turned her into an avatar. And then they are now using that to produce that hyper-local forecast content in partnership with essentially the Canadian version of Home Depot. It's called Home Hardware, but same concept, big box home deal. So the idea is that, hey, it's going to be a warm, sunny weekend in Holly Springs, North Carolina. It's a great weekend to get out and overseed your fescue lawn and head over to Home Hardware. They've got the seed and the fertilizer and everything that you need. Or it's going to be a cold, rainy weekend. It's going to be a great weekend to do that painting project inside. That can be done at scale on demand. If you think about this pre-AI, somebody would have to record every possible iteration of that, which of course is not realistic. So now they're able to partner with a company to create these hyper-local forecasts and to dovetail that with sponsored content, which is a way for the company to make money and to drive traffic to a key advertiser. And then, of course, thinking on overseeding and grass and everything else, there's just ChatGPT and other large language models. You can feed in the forecast and feed in maybe some knowledge about what it is that we're working on. Hey, you give me the forecast. I'm not even giving it the forecast. I'm going to make it go get it, but I'm telling it I live in Raleigh and do I need to actually water the grass? So not only we're sort of bypassing the forecast step. What do I need to do with that forecast information? What's the takeaway? Do I need to actually change my plans? And of course, ChatGPT is more than happy to go and find the forecast. I actually clipped that out, but it gave me a 7-day forecast for Raleigh, and then interpreted that forecast and gave me specific directions on what I need to do to keep my little grass seedlings going. So that's a really interesting thing. That's here today. Like, anybody can fire up ChatGPT or Claude or anything and do something like this right now with forecast data. So for those of us who are in the human business of communicating, this is a really interesting challenge for us. What's our value? How do we add value in this space when the computer could do it? Now, you're assuming that it knows what it's talking about. Does it actually know how to grow fescue seed in North Carolina in October? I don't know. We're putting a lot of trust in it. But it can do it, and it looks pretty impressive, which is the really interesting thing. It looks impressive, and if you don't know what you don't know, you don't know what you don't know. You're going to take this as gospel, you're going to act on it and go from there. So the next question, of course, is it any good? So we can run the models and it runs fast and da-da-da-da-da, but is it actually worth doing? And the early results are an unequivocal yes. So this is the European. We're comparing the AIFS to what they call the IFS, which is their internal term for their model. And lower is better. And notice the AIFS, that darker black line, is lower in both of these. These are just a couple of parameters that we use to look at the overall accuracy of a model. And so even far out, it is substantially better, significantly better than the physics-based model. So let's look at GraphCast. This is Google's option. This comes from their paper, Lam et al. From 2023. Again, lower is better on the first two graphs, higher is better on the right. And of course, GraphCast HRES is the way Google talks about the Europeans model, but GraphCast exceeds accuracy in pretty much all cases. And if you look at the bottom, it looks at a number of scorecards of various variables at different atmospheric levels and different lead times from 1 to 10 days. The sort of bluish mauve color here is better and red is worse. There's a lot of blue on that map, a lot of that purple color. So yes, GraphCast is exceeding the physics-based models pretty healthily, and it's doing it in a much shorter amount of runtime. And then this is GenCast, same concept, lead time on the x-axis, different vertical levels on the y-axis. A lot of blue on here. GenCast is doing really well. And then this is something that I added to the presentation literally last night. Brian McNulty, who's a professor at the University of Miami, researcher, was running some stats on this year's hurricane season. So we have Melissa now in the Caribbean, but up until Melissa, through the L storm, he had run some basic verification statistics on this. And I'll call out a couple of things. The diamonds are the 5-year average, and this is what that cone of uncertainty is based on, that 5-year average. So you have that. And that's sort of the baseline. Notice that most of these model tracks, OFCL, the red one in the key in the top, is actually one of the more accurate ones in the mix. It's hard to tell, but it's closer to the average. That is the official Hurricane Center forecast. And so we're looking at the Hurricane Center forecast along with a number of the other model sources. And then GDMI is the Google DeepMind model. And notice that is the line that is the lowest, the least error. So the Google DeepMind model, on the average, has beat everything else, including the official Hurricane Center forecasts, which are really, really good. So this is for a track verification. And then intensity, bit of a sticky wicket. That's one of the interesting sort of forecast challenges that meteorologists are trying to solve. This year has been particularly not great, but you can see the average when the diamonds been down below, and the Google DeepMind model is pretty much second place compared to or first place if you're not counting the average. So the Google DeepMind model, just as an example, is already doing a really nice job. And if you remember back to the two storms that were doing that dance off of the southeast coast, Google's GenCast was actually picking up on that turn out to the east before most of the physics-based models, about 18 hours ahead of the physics-based models, picking up on that dance and that turn out to sea. So yes, there's clearly some value. So this sounds great. Model runs in 8 minutes, full ensembles in 8 minutes. It's better than everything else. Like, let's throw away the physics-based models and move on to AI and just, I'm here for my AI overlords. What's the catch? Well, AI has to be trained. Like every AI, we have to train it on something. And as it turns out, the Europeans have come up with something they call the European Reanalysis ERA 5. This is the 5th generation of this. This is a data set that they've gone back and reanalyzed the data, all of the weather data, at a 31-kilometer resolution, 137 vertical levels, hourly time steps, going from 1940. They started with 1979 to current, and then they backfilled the catalog all the way to 1940. So basically, going back to prior to World War II, we can go back and look at the data in this kind of temporal and spatial resolution, and we feed that in to the models. Now, my meteorology students here know the catch with that. A lot of the really interesting weather that we really care about happens at grid scales that are much smaller than 31 kilometers. The average thunderstorm, for example, would not in its wildest dreams fill up a 31-kilometer grid cell. So the AI models, yes, we're capturing that, but from an information science standpoint, we do not have the resolution here to capture these things directly in a truly coherent way. The other thing is, I'm not sure if you've noticed, but the planet has gotten a little warmer since 1940. we've seen a steady progression in the amount of CO2 in the atmosphere that is causing changes tangible changes to the weather that we can see and measure today that have been happening over the last few decades and really going back to the 1800s. So between those two, we have a data set that's really useful, but it has some serious limitations. It's got some serious blind spots in it. So that's a problem. So for the reason that we look at Google DeepMind for things like hurricanes is they're big scale critters. This is a big storm, and the model's going to capture it pretty well. But if we wanted to talk about perhaps a tornado outbreak, this is the tornado that hit Joplin, Missouri a number of years ago, killed almost 200 people. The model's not going to capture this in any sort of this kind of detail. It might know that there's weather there was a bigger system that drove this, but the specifics it's not going to have the first clue about because, again, the training data set just is not there right now for that. And then on the comm side of this, are people comfortable with getting bad news like, hey, there's a tornado heading for your house? Are you comfortable getting it from an AI avatar? Hollywood, this was blowing up the news last week. This is Tilly Norwood. She does not exist. She is a figment of AI's imagination, but she's an actress. She's up for hire for your next project. And Emily Blunt and a number of others, Scarlett Johansson, pushing back on this, in part because this is a threat to their careers, but in part because, hey, this is a soulless thing. It has no human experience to connect with. There's not human here. There's a whole big thing. I'm not sure how many of you follow The Oatmeal as a comic. It's a web comic. It's really funny. It's a bit out there in terms of the humor. It's a bit blue, but it is a funny comic, really thoughtful. And he recently just did a comic about AI art. And AI, like we think about art and creativity as something that's a human endeavor. So when you hand it off to a computer, like, what is that, right? Is that truly art in the way we think about it or not? Same thing here. Like, do you want to get that cancer diagnosis from an AI avatar, or do you want it from a human being who can hold your hand and tell you what your options are? Like, I know what I want in that, but I'm also, an elder millennial, young Gen X. I'm in that Oregon Trail generation, proud Card King member of the Oregon Trail generation, and don't call them Zennials. It's Oregon Trail. So thanks for coming to my TED Talk. And I would much rather have a human deliver that kind of news to me rather than the other way around. So let's put a bow on this. I go back to the fact that meteorology and computer science are so inexplicably linked. And do I think of Moore's law? The computer scientists in the room know this one very well. The doubling of transistors you hear different versions, 18 months or 2 years. The idea is that this is a log plot of the amount of transistors on a microchip, and you see we got lots more transistors, we have a lot more capacity into the computing technology now. So as it turns out, meteorology has benefited from that in large part, not just to numerical weather prediction and better models and more compute, so we can have finer resolution on the models and better physics and more accurate numerical approximations of these partial differential equations. But we also generate out of that, we have better computers on board the satellites that can capture more data. We have better processors on the radar that are capturing the radar data and putting that in. We have better QA on just observation data in general. So we have benefited from that significantly, and I'll show you two graphics. This is the historical accuracy of forecasts, the solid lines in the northern hemisphere. And you can see that compared to 1981, a 10-day forecast in 2018 is almost as good, about as good as a 7-day forecast was in 1981. We've seen that kind of growth and that kind of improvement in accuracy. And of course, the shorter the lead time, the more accurate they are. But I'll draw your attention to the fact that especially that 3-day forecast and the 5-day have really started to sort of approach an asymptote. Have we flattened out? Have we hit the predictability limit that Edward Lorenz came up with when he was thinking about chaos theory and doubling time, the idea that forecast errors would double every 5 days, and so that put a lid on how accurate or how useful a forecast could be the farther out in time. He sort of pegged it initially at 2 weeks. A little later in life, as he was reviewing his stuff, maybe he softened on that hard date a little bit. But generally, we've thought about 2 to 3 weeks as the useful limit of specific weather predictions. So I would ask the question, Am I okay with a 40% accurate 10-day forecast? Is that enough utility for me to recognize that there's uncertainty in that, obviously, but that's twice as good as it was, 30, 40 years ago? Maybe that's useful enough. It's good enough. But can we actually bend that curve? Does AI give us the ability to bend that curve either by itself or married with physics-based models? And then this is another one. Think about high impact weather. This is the National Hurricane Center's forecast track error over the last 50 years, going back to 1970. And notice that the blue, which is the 120-hour, 5-day forecast, that forecast today is a 5-day forecast is almost as accurate as a 1-day forecast was 50 years ago. So again, meteorology has benefited from not only improved observation techniques, improved modeling techniques, improved forecasting techniques. A lot of that is driven by technological innovation, and we have benefited from that because it costs a tremendous amount of money to evacuate even just a mile of coastline. And so if we can shorten that amount of coastline we have to evacuate, we're saving the economy a ton of money. And as we learned in Hurricane Rita, we lost more people evacuating from Hurricane Rita than Hurricane Rita directly killed. So it's really important if we can really narrow down the number of people we have to evacuate or the number of people we have to disturb for ahead of some kind of weather. That has real direct, not only monetary impacts, but also life impacts. So the more of this we can do, if we can, we're sort of approaching an asymptote here. Can we bend that a little bit further? Can we squeeze out a little bit more? Or can we start doing out forecasts 7 days, 10 days, 14 days that would have the same utility as a 3-day forecast 50 years ago with the same caveats and uncertainties and that sort of thing, but is that useful? Could that be useful to emergency managers and planners? I think it would be. Does AI hold the key to that? And this going back to the table from Shin et al., look at some of these models, 7 days, 6 weeks, 5 days, 7 days, 72 hours, 1 to 2 weeks. There's one climate model that's going out 10 years. They're not actually predicting day-to-day weather out to 10 years, but looking at climate 10 years, day-to-day weather out to a month. So we have some of these entrants in this space that are actively trying to push the limits of predictability to see if we can squeeze out more accurate forecasts beyond that sort of 2-week boundary. So some closing thoughts. Number one, how can we leverage this technology to advance forecasting, to either give us more accurate forecasts, more precise forecasts with the same level of accuracy, better forecast out to a longer period of time, et cetera, et cetera. That's sort of the fundamental question that we're here to ask. What role is physics-based modeling going to play? Do I need physics-based models to run out 2 or 3 weeks when the AI is generally better at coarser resolutions? Can I get the same sort of bang for my buck with a lot less compute, a lot less stress about all of that? Is there a place for a really neat blended approach where we're used to in numerical weather prediction, we'll have nested grids. So you'll have a grid that may be global, and then you'll have a focus area over the continental United States, and then you might have another nest inside of that. Is there an application where, and you would usually have better resolution for the smaller nested grids, do we let AI run the background and then run the physics on the more fine resolution where we can't really trust AI because it doesn't have the training data? Is there a potential for a blended solution here? Obviously, training AI, if you're thinking about a single processor, this is a years-long process. You throw 36 of these at it, and you do it in a couple of months. That's still a lot of compute. There's a pretty significant environmental impact on that, right? In terms of electricity, water use, all the things that are hitting the press these days. What are the compute trade-offs? Well, if I could stop running this global model that I run for probably 12 hours of compute a day on the same number of cores that I would run an AI model on and run it for 8 minutes, but I have to spend 2 months training it. Like, where's the trade-off for that? Of course, how do we train AI for a changing climate? If the AI is only as good as the data it's trained on, our forecasts will have that uncertainty baked in from the beginning. Is there a way to account for that? How do we, again, handle smaller scale events, things that are going to happen within the grid spacing of the whatever training data that we're feeding it. There's a really interesting project NVIDIA is working on where they've done a 2-kilometer resolution global grid where they're essentially running simulations of weather, and then they're going to train an AI on the simulations. So it's a really interesting concept, and I'm not sure how that's going to go. But it's an interesting, like we don't have the training data at 2 kilometers, so they're generating it just by running the model over and over again and coming up with plausible scenarios. Will that be interesting? I don't know. I'm looking forward to seeing. One of the things that challenges us in the meteorological space is how do you address a black swan event? The model is predicting a severe weather outbreak in Alabama in April of 2011. And we saw it, we knew it was going to be a high-end event, and they were able to ring the bell. Do we know enough to trust the AI to be able to tell the difference between what we would call a hallucination or an actual black swan event like an April 27th, 2011, or a Hurricane Katrina, those kinds of things? We're still exploring that. And then finally, can AI bend the accuracy curve? We're flattening out, almost as Ed Lorenz predicted we would 60 years ago. Can we bend the curve? Can we actually bend that back up? I don't know. I think there's some really interesting possibilities here, and I wouldn't be a good technologist if I didn't say yes. I think it can, but we're not there yet, but I think there's some really interesting possibilities here. So I will challenge you with that as you're going through your day and through the rest of your careers. Is this a place where you can drive not only monetary benefit, but also life benefit by helping us come up with better AI models? I don't know. Thank you very much. It's a pleasure to be here.
Do our students have questions for Nate?
I have a professor who was talking to me about AI and was saying that the traditional forecasting that's done like at National Weather Service or SPC, NHC, that's more and more going to be replaced by data analytics, trying to manage and feed into the AI models. So he said that, quote, traditional forecasting is dead, which sounded pretty dire to me, but I'm not sure, would you agree with that or say that's too much?
That's a bold claim, but I think there's something to it. And I would say that the days of going into a weather service office and spending 8 hours churning out a forecast and really analyzing the data, those days are over. And they have been for some time. And the Weather Service will tell you the way that they run something called the National Blend of Models, where they take all the physics-based models, they put all this in a bucket, and we come up with guidance, numerical guidance. And the Weather Service offices generally have been told days 4 through 7, you're more likely to make the forecast worse if you change it than if you just leave it as is. So we're already seeing that sort of guidance. Now, in terms of forecasting, is there still, we still have to understand the atmosphere. Somebody has to understand the physics of how the atmosphere works to be able, again, is that a hallucination or is it a black swan? We have to understand the underlying meteorology to be able to figure that out. So forecasting will be different, but I don't think it's going away. I think it is going to be a lot more of managing the automation, QAing the automation, understanding when the automation is going to do well and when it's not. And if you think about that, that is the same problem that we have had with any kind of new technology since we've been doing technology. And I'll give you an example. The washing machine. When the washing machine was invented, did we stop having to wash clothes? Did it just that work just magically go away? No. There are some things we don't put in the washing machine. I'm not allowed to put my wife's pants in the washing machine because I shrunk too many of her maternity pants back when we were having kids. But there are some things that we do. You manage the automation. The work has changed. You still have to know how to do it, but I'm not standing out in the front yard with a washboard, washing things by hand and then hanging up on a clothesline to dry. Is that better or worse? That's for you to decide, but forecasting will definitely be different, and we're already seeing that, even before we start talking about AI.
Very interesting, great analogy. I think you had a couple more, and I know we're kind of short on time.
Right.
So, okay. thought I was close.
I got all night, so.
How much of an issue are, like you mentioned, hallucinations in these AI-based weather forecasts, especially when you have, you mentioned, I think the phrasing you gave was moving the models, where you have take the previous model,
Cycling the models, yep.
Cycling,
Yep.
plug it back into a future model run. How much of an issue do hallucinations play a role there?
I'm gonna answer your question with a very weird answer, but it's gonna make sense. Are you meteorology or computer science?
Meteorology.
Okay. So the amount of model data that meteorologists look at, not only do you have the American model, you have the HRRR, you have the HREF, you have all the European model, you have the German Weather Service has a model now called ICON. There's a ton of different models out there. And there's a saying, all models are wrong, but some models are useful. And I think that is a really good way to approach even your generative AI. We're so used to looking at bad model data, right? Like some of it, it's all wrong. Some of it might be useful. Some of it might be helpful to get us to a forecast. And so I think meteorologists especially are well equipped to handle the hallucination problem because we're so used to the GFS spinning up double hurricanes making landfall in North and South Carolina 10 days out, and then one model run later, it's gone, right? So we're used to this. It's something that we deal with all the time, and we look at that, we know you learn the proclivities of the model, you know the temptations, we know the GFS has a problem with this. So when it does that at day 10 or day 14, we go, really? Would we say that? No, and we discard it because we know the underlying physics and we can look at other data sets as well to go, yeah, the other models are not picking up on this. We know this is a tendency you have. We're going to wait for another model run before we hoist the evacuation flags. So yes, I think hallucinations are going to happen, but we're so used to the GFS and even the European hallucinating, it's just another bad model run. Yes, ma'am.
Comparing these AI models to the existing physics-based models, how do the maintenance and energy costs stack up between them, and who bears the burden or stands to benefit from those changing costs?
So great question. Right now, up until really 10, 15 years ago, modeling, much like satellites and radars and other things, were such a huge investment in compute time that only large entities like governments or government consortiums could run computer models. And so the GFS and the previous iterations of models before were all run by the federal government. The European model is run by the European Center for Medium Range Weather Forecasting. It's a consortium of European governments that have all pooled money to run this sort of world-class model. The Germans have something separate, the Japanese have, the Canadians have stuff. But generally it's government stuff. In the last really 20, 25 years, we've now seen the advancement of compute get to the point where non-government players can jump into that. So IBM is running the graph model, for example, and there are many others. So those companies, those entities would stand to benefit in the event that we're able to reduce the amount of compute time. What we found, though, is really interesting, is that we tend not to, we don't look at the saving money piece. We look at that as, oh, I can run this model at this resolution at this time. If I throw more compute at it, I can, or more efficient compute, maybe make the algorithms cleaner so that they run faster. We'll just run the model out 2 more days, or we'll increase the resolution. So what we found is that people are not interested in saving money or energy. They're more interested in trying to run the model further out. Having said that, the amount of time and compute it takes to train these models is significant. It is not to be sort of discarded. But if you find a model that you can train and then run over a long period of time, you will recoup that, because instead of running the GFS ensemble for 3 or 4 or 5 hours, you're running it in a minute. So if you, or 8 minutes in the case of GenCast. So if you're able to run it in a much shorter amount of time, then you eventually recoup that training cost. So if you're not training new models every year, you will have an opportunity to recoup that investment and eventually wind up ahead. But the question is whether or not we're interested in that, or whether we're going to just run the model out farther. And you saw with some of those examples, they're running them out, multiple weeks to months to try and, again, push the limits of predictability and see what we can squeeze out of that.
so much. You all have great questions. That was great. Nate, we are so thankful for your time tonight. Really
My pleasure.
appreciate it. Let's give him another round of applause. We all deal with weather, so it's always interesting.
Right.
And if you're local to Raleigh, you know about the Raleigh Weather Dome that we have here.
What I find traveling around the country is that every city has a weather dome. It's not just us.
Right? I was going to say I'm really interested to see if it performs better or worse AI in situations
Right.
like this. Thanks again, of course, to our sponsors from Labcorp. We're really appreciative of that. And for those of you who need the credit for seminars, certainly we've got someone over on this side. If you're a PhD student, I'll be glad to sign forms in just a second. And there's a form online for our web folks. We do have a small gift, a token of our appreciation to Nate as well that's in here. But we really just, it's a photo frame. We'll have some photos for
Thank you.
you for tonight to share as well. So you can document that. But certainly, I think if you've got a few minutes,
Oh, yeah.
students want to walk up. Yeah. So if you've got another question, come and chat with Nate. And again, thank you all for being here. We hope you will join us again in February with our next speaker series. Thank you.
Thank you.
That was excellent.
Thank you. That was fun.